Now this circuit here is very, very simple, and effectively what we have is our power source, which might have an EMF perhaps of, I'm going to call it V0, so that's V0, and maybe this is connected up with a switch to a capacitor. Now effectively if you have a battery and a capacitor, what it's going to do, it's going to charge it up until the potential difference across this component here is equal to the potential difference across that. And that's just from Kirchhoff's second law, saying that the EMF is equal to the PD around that closed loop in the circuit. But what we can then do is we can take this switch and we can basically flick it over to this position over here. So we've turned the switch over, we've opened this part of the circuit, and now what we have is a circuit with just a capacitor and a resistor. Now this kind of circuit is called an RC circuit. So RC isn't radio controlled, it is a resistor capacitor circuit. And what can then happen is that this capacitor will then discharge through the resistor. And we can look at maybe perhaps using a voltmeter or some other kind of sensor at how the potential difference changes with time, how the charge in the capacitor changes with time, or how the current in this part of the circuit changes with time as well. Now there are two things that effectively alter how quickly things discharge. First of all, if you have a bigger capacitor, then this is going to affect how much charge is available and how quickly that flows. And therefore, the time it takes to discharge is going to be dependent upon the capacitance of that circuit. The bigger the capacitance, the longer it takes to discharge that capacitor. The other thing it depends upon is the size of the resistor. And this one here is a ceramic resistor, so it still resists the flow of current, but it's not maybe one which has colour banding around it. And effectively, if you replace this with a bigger resistor, maybe greater than 10 ohms, the bigger the resistance, again, the longer it's going to take for the charge to flow through that. And what we can look at then is something that we call the time constant. Now the time constant has a symbol tau, and it's going to be dependent upon the size of the capacitance and also the size of the resistance. And this time constant is equal to C multiplied by R. And this thing here, alongside this circuit here, is a really good example of where we have an exponential decay. Now this graph here shows an exponential decay, and effectively it's a line in the form of y equals e to the minus x. What is exponential decay? Well, these things happen all the time in nature, and effectively what it's got to do with is the ratio of how much something changes over a certain unit of time. Now, as a way of explaining that, what we can look at is the ratio of maybe how something changes with respect to time. And what you can see along here is we have an even, perhaps, time interval. So this is going to be my time along the x-axis. What I can then look at is the ratio of how 1 compares to 2. And perhaps maybe this is our value of, I'm just going to call it x, okay? Effectively, what we can say then is that x1 over x2 is equal to the same proportion as x2 to x3, which is equal to x3 to x4. Now, an example of this maybe could be perhaps radioactive decay. It could be perhaps maybe a spring that's oscillating, and every time it oscillates, it loses maybe 10% of its energy. So every time we have one cycle, it maybe goes down by a factor of 10% each time, but that's 10% of the value that it was at the previous point. But basically, if you do mathematics, you know all about exponential functions. If you're not sure, I do have a video which is all about it. Now, when we look at something maybe with a capacitor, what we find is we have an exponential decay. And effectively, what we can look at is the value of x is equal to the original value x0 times e to the minus t over CR. Now again, this CR here is equal to our time constant tau, and effectively time over time, which has this has units of seconds as well, is just a dimensionless quantity. And this is our original value. Now it doesn't matter what x is. For example, x could be equal to the current flowing in that circuit, it could be equal to the potential difference across a capacitor, or it could be equal to the charge stored on that capacitor. And effectively that means if we want to know maybe the time, or maybe we want to know the current after a certain amount of time, we can say that the current flowing is equal to the initial current that flows multiplied by e to the minus t over CR. And this basically allows us to plot our exponential decay of the current, the potential difference and the charge of a discharging capacitor. So this time constant for a discharging capacitor tau is equal to the time taken for the PD to fall to 37% of its initial value. Well then, it's, why is it 37%? Well, effectively, what we need here is when you have the time constant is equal to this time t, then that's effectively e to the minus 1. And if you work out e to the minus 1 in your calculator, you find that the value is about 0.37. And therefore, when you have a 37% of the original value, that's equal to the time constant. And effectively, the greater the time constant, the bigger the capacitance, the greater the resistance, the greater the time it takes for that potential difference, or indeed the current or the charge, to fall to 37% of its initial value.